it is not performing the same experiment n times on the same box. It is not. You know very well why. Once we measure the momentum of a particle, and you will find a value, and next time it will be that value again, because the wave function was something. Once you do the measurement, the function will change and will collapse, and then it collapses into one just single value. Next time you do the experiment, you will keep getting whatever the value. Let's say 2 kg meter per second. So you will keep getting, let's say, 2 kg meter per second, 2 kg meter per second. So it's nonsense after that. It's the same value, okay? So that way, yeah, your answer is this one single value. The first value that you got, you will get that n times. So that's why you have to make n copies so that one experiment doesn't affect the next one. So, particle in a box to start horizontal moi, but infinite potential. Itu next unitot moi continue korim. Time independent. Schrödinger equation. Okay. So কি আছিল আমাৰ equation to hold our complete Schrödinger's equation. Also, if we deal with systems that has only space-dependent potential, there is no explicit time dependence in the potential, then we can have solutions that can be separated in space and time part. By the way, this is one-dimensional Schrödinger equation. In space and time part, and we have seen that if we substitute this, then this equation splits up into two parts. One is h 1 over phi of t, del phi t, del t equal to this part. Equal to a constant, okay? A constant that we named E. We yet don't know what E is, okay? But at least it has to be a constant, because this piece is only t dependent, only, and this piece is only x dependent, and therefore they're independent, still equal, so they have to be equal to this constant E. Okay, oh, I forgot the duster. Okay, so this is our case. And in that case, so this piece becomes equal to E, and then we can find the solution, at least of this part, to be e to the power minus I E t by h cross. Okay? And then we are left with only this piece of the equation. And this is our time-independent Schrödinger's equation that we will be solving, okay? And the important part here is that what is the justification of this separation? So we will talk about this a little bit because this is important. So
psi to x dependent atau phi to time dependent. Ini atas x atau tidak ada independent lagi.
yes, independent hobo. So basically it takes the form psi x e to the power minus I e t by h cross. E dependent in a very special way. Okay, the t part to E dependent only in this form. Okay. Now one important thing is that this mod psi x t square. So let's discuss some properties of this particular form. Okay, these are called stationary states for a reason. Stationary means what? They don't change in time. But clearly they do, right? There's a time dependence, but a special way. This piece is what? It's just oscillation. This is what? Sine et by h cross plus I cos et by h cross, right? So it has both real and imaginary parts, and they oscillate. So first of all, one, stationary. What do we mean by that? So we assert that mod psi xt, mod psi squared, is actually mod psi x squared, and the time dependence goes away because here we have minus I e t. But this we are saying will be 1. But how, why, I mean, how does it have to be 1? Like exactly how? Because if E is real, then of course this term is 1. Because this is just what? E to the power I minus I e t by, so this is mod this square, right? Times, so this term, it is e to the power minus I e t by h cross, and then e to the power plus I e star t by h cross, right? Usually. Just this into complex conjugate of itself. That's mod square. Now, if E is real, then this into this, E star equal to E. So, if E is real, then E star equal to E, and this cancels out, and we have just mod psi x square. Now, this is a proof that I will give you that take E equal to some real part E naught plus I into, or let's say ER, and I into, oh, that notation will be there. The E naught plus I into gamma, let's say. Okay? Take this and then put it in your form. So then, you know, psi xt equal to psi x, and then e to the power, this becomes I e naught, and e to the power what? I and I minus e gamma t by h cross. Okay? And then prove that to maintain this condition, Remember normalization condition. This is equal to 1. If this has to be true, then show that your gamma must be 0. Okay? If normalization, show that this for all time, for all values of t, if this has to be maintained, then gamma must be equal to 0. For all values of this has to be maintained is what? Time derivative of this piece has to be 0, right? The dt of this has to be 0. And therefore, gamma has to be 1. So just, you have to prove that. It will be a simple proof. And so what it means is, the conclusion is that this then just becomes not only just this probability density becomes whole wave functions mod square becomes just the x piece mod square. So that means probability does not change with time. Okay, probability density does not change with time. When the wave function is in this particular separable form. Okay, in this particular separable form, that is when our psi xt equal to psi x e to the power minus I et by h cross. Okay, and that's why, and you can also prove that not only just the probability density, but also any expectation value. So expectation value of x, p, or anything, let's say some function of x and p, so which is dx psi star x t, and this q of, and of course the operator of momentum. Remember, what was the momentum operator? It was minus IH cos del x. Function of this is the operator, anything. This could be kinetic energy. This could be anything, okay? That's the expectation value definition, right? This also does not. Ki? P mane? হয় নহয় a q for example Hamiltonian হ'ব পাৰে or kinetic energy হলে কি হ'ব এটো p square by 2m হ'ব or position হ'ব maybe or position or square or position into momentum, any operator, any variable that we measure, any variable that we measure physically, quantum mechanically it corresponds to an operator. So position x is x. If it's momentum, it becomes the momentum operator that acts on our wave function. আমি আরো details of এটো আলোচনা করিম actually. So when we measure, so in quantum mechanics, we have an operator corresponding to position. We have an operator corresponding to momentum. These operators act on the wave functions and give us some values. Okay, so we calculate the expectation values of the operators this way. The operators sandwiched in the middle, psi and psi star this way, and this gives us the expectation value of the physical variables. So if we are looking for what, if we do some measurements, then what is the expected value of the momentum that we must get? So this means if you perform experiments and measure momentums on, let's say, some n number of same copies of the system, okay? If it's a particle in a box, let's say n number of particles in n number of boxes in same condition, same state. And at the same time, you do experiments on all this and you get some P1, P2, P3 up to Pn values. And if you calculate those averages of your experiment, so it's sum of Pi divided by n, that value of your experimental average will be close to the expectation value that you calculate using the operator acting, that operator. So in this case, it will be the momentum. So it will be this minus I h cross del x sandwich between psi and psi star. The value that you get, that's the ideal theoretical value, the expectation value. So if your number of particles in a box goes to infinity, then that experimental average will match with this average of your momentum's expectation value. Okay? So be very clear about this. Keep thinking about this in this way, okay? It is not performing the same experiment n times on the same box. It is not. You know very well why. Once we measure the momentum of a particle, and you will find a value. And next time it will be that value again. Because the wave function was something. Once you do the measurement, the function will change and will collapse. And then it collapses into one just single value. Next time you do the experiment, you will keep getting whatever the value. Let's say 2 kg meter per second. So you will keep getting, let's say, 2 kg meter per second, 2 kg meter per second. So it's nonsense after that. It's the same value, okay? So that way, yeah, your answer is this one single value. The first value that you got, you will get that n times. So that's why you have to make n copies so that one experiment doesn't affect the next one. It will collapse the first box, but not the second box is untouched. So second box, the value will collapse into some different value. The third box into some different maybe. Okay? That way, it's like you are performing the experiment n times on the same quantum state. And if you keep performing in the same box, then it's not the same quantum state. First time it was the original state. Next it's changed. Okay? Okay, this is the gist of quantum mechanics actually. This is the strangest thing about quantum mechanics. Experiment is everything. Okay, so now next thing that I'm asserting is that it's not just probability density, so that stays, you know, time independent. It is also the expectation values of all dynamical variables. X and P dependent, all variables, their expectation values also remain unchanged in time. Which means what? Even your this thing will become just simply psi star x and this. The variable, whatever it is, a function of position and momentum operator, psi of x. So x of the full wave function, you don't need anymore. Just the x piece is enough. And that's why, so what that means is ddt of expectation value of xp, simply let's say, will also be 0. So the expectation value of any dynamical variable does not change with time. And that's why they are called stationary states. Okay. Now we are going to talk about what that E was. That constant E, remember? For that we need the equation. So the time-independent Schrodinger equation, remember, was this. I said H psi equal to E psi. Just the X part, where the H was the Hamiltonian operator. P square, P operator over 2m plus V of X. Right? If you put the value of P operator, which is so I write them in operator form. So H psi is equal to E psi. The eigenvalue equation, remember? Okay, this is our time-independent Schrodinger's equation in 1D. Okay, so we need this. So let's see what is the expectation value of Hamiltonian. So expectation value of Hamiltonian is actually the expectation value of total energy, right? Because that is the classical variable that we are going to calculate the expectation value. Right? So psi xt, and then put h in the middle, star psi xt. On what? On the stationary states. So dx, and this will become just psi x star phi star xi t, and then h in the middle, psi x phi t. Okay, so expectation value of energy, total energy, then becomes, okay, so remember, what was your phi of t? E to the power minus I e t by h cross. And I said that E must be real, and that part you will prove. You will prove that easily. So which means the phi from here will go away, okay? And phi can come out in this direction, I mean out of this, because phi has no x dependent. In your x is a function of x and p, okay? So this part will come out, and therefore what this phi into phi star will cancel each other out. So what we will be remaining with is psi star x h of psi x, okay? And what was your h operating on psi x? It was the time-independent Schrodinger's equation. Remember, h of psi x, h operating on psi x gives us this constant into psi x, right? So I can use time-independent Schrodinger equation to get the value of this thing, which is nothing but a constant into psi x. So that means just E is a constant comes out, and this is nothing but psi star psi, which is mod psi x squared, right? And this thing, what is the value of this thing? Yes. The value of this thing is 1 because you normalized it. And therefore, this is E. So we see, okay, expectation value of total energy, which is expectation value of Hamiltonian, is E. But that, yeah, okay, that can happen. That does not mean that the energy corresponding to the state is exactly E. It just means that the expectation value of E. So what does expectation value mean? If you have some distribution of values, you have probability, you learn probability even in your thermodynamics, thermal physics, you know that this means this value is, let's say, expectation value of energy equal to E. Okay? It means this mean value is E. But there could be some variation, So if you measured on n number of boxes, sometimes you will find on this side, sometimes on that side. On the average, if you calculate the average for infinite number of them, you will get E. Okay? That's okay. That's fine. So we get the expectation value of energy to be E. What is E? That constant. We yet don't know what that E is. Oh, by the way, the expectation value of energy equals to E. So E is, of course, energy. Now, let's calculate the expectation value of H square. Okay? So by this same logic, let's say, dx psi, same logic, again, only the x will remain, okay? The phi's will cancel out. So H square, so which means H and H twice operating on psi x. One time H operating on psi x will give us E psi, right? And then E will come out and you are left with again another H on psi x. Okay, so let me just somewhere save this thing. Expectation value of energy to be equal to E. Once again, this is just E psi x. Therefore, it will be E square and dx mod psi square. So, which means E square, right? So, expectation value of your H square is E square. Okay. Now, what does that mean? That means if we calculate the variance or variance is given by sigma square, and it is expectation value of E minus, actually in original definition it has to be this. So it is the expectation value of deviation from your mean, which actually becomes, from, no, sorry. Let's write this that way. Which becomes expectation value of H square minus square of expectation value. This equals this, but originally this is the definition. How much it deviates each value from the mean value. That's the measure of the variance, okay. And you see that, okay, this is E square, and this is E and square. So this is also E square. That becomes 0. Which means for this particular distribution, every value is E. There is no spread. It's exactly this, E. So every measurement on this kind of, stationary state, the psi xt is equal to psi x times phi t. This kind of states, stationary states, if you perform an experiment, you will always get the value E. There is no spread. It's not just the expectation value, every value is E. Okay, So it means, that really means that every stationary state given by psi x e to the power minus I e t by h cross has an unique E, and this E turns out to be energy. Because we just proved it. It is the expectation value of E, and there is no spread around it. So every stationary state, what is stationary state? That we can write as a multiplication of a space part and a time part that satisfies complete Schrodinger's equation for a time-independent potential Vx. If this is so, then such states will have a definite energy. If you perform an experiment, it will always give you this value E. There is no variation. So if you take 10 boxes, and if the state of the particle is like this, right? A state will be given by a wave function, right? A particle has a wave function. If those wave functions are in this form, then you will get a specific value E in for each box. There is no E1, E2, E3, there is no spread, just one constant value. Whatever that value is, it will be single value. And that's the reason actually we chose this time piece equal to space piece equal to E, the name E. Why we chose that? Because we knew that this will come out to be energy, then why not use the, symbol for that. Okay, so we learned two things about our stationary states. That the probability and expectation values remains stationary in time. And they have a specific energy. Now let me talk about the third specialty. So this was a very special kind of solution. Right. Turns out that if you knew psi x, you can actually write any general solution in terms of them. So in general, what happens is, you get, when you solve the time-independent Schrodinger's equation, del square h cross square by 2m psi x del x square plus vx psi x equal to e psi x. When you solve them, you will see that often you get a series of solutions, which means some psi 1x, some psi 2x, some psi 3x, and so on, some infinite. Okay? Usually these many solutions you get independent. And that means, and it happens that any function you can write in terms of them. I told you, it's just like Fourier expansion. So any function you have, you can write in terms of these solutions of time-independent Schrodinger's equation. And even more special is that you can get the most general solution, psi of x and t. All you have to do is just plug their individual time part. What is time part? This thing. This is called a wiggle. Wiggle means this. This is an oscillatory function in time. So all you have to do is n equal to 1 to infinity Cn psi n x times their individual. So each one, remember, we saw that each such solution has a particular corresponding fixed energy. So psi n x corresponds to that, corresponding to that, there is a particular energy. So if you take psi 1 and its particular E1 P over H plus psi 2 and multiply it with some constants and you adjust them, take psi 1 a little bit more, psi 2 less, psi 3 maybe more, that one negative. This way you can take all of them and you adjust, each of the individual coefficients are like knobs, okay? And it's like a music. So basically these are like saregama, okay? These psi n's are like your sargams. So you can produce by adjusting which one should go up and which one less. This way you can adjust them and produce any music you want. So in general, so that's your complete solution. So that means if you knew the solutions of time-independent Schrodinger's equation, these will be a series of psi 1, psi 2, psi 3 functions, and for them, there will be a series of corresponding e to the power minus e1 t by h cross, e2 t by h cross, and if you plug them and chosen your constant wisely, you can make whatever general function you want. But of course, within that space. What do we mean by within that space? Whatever that x varies. So for example, if you are doing for a particle in a box, then x varies from 0 to L. So your function, this function must be valid within that. So this function will also be valid between 0 and L. Okay, if you're doing it for some free particle, let's say, then it's valid from minus infinity to plus infinity. Then this will be also a function within that range, any function within that range. Okay. Okay. So so that means it solves our problem. Although these solutions were very special, these were psi n e to the power minus en t by h cross, right? This form psi x into phi t. Turns out you can add a lot of them and get a general solution that is not separable. So now look at this. This sum cannot be written as, in general, cannot be written as sum f of x into g of t. You cannot anymore, right? It will be what? Some function of x into e to the power minus some, I don't know, 1 t by h cross. And then plus sub sine 2x e to the power minus, some 2 minus 2 et by h cross I. Okay? And then if you do this sum, that sum cannot be written as a separate piece of x into separate piece of t. It's easy to see, right? But then that means what? We got a solution that is not separable out of these separable solutions. So it solves our problem. Although we started with a very special kind of solution, we can actually generate any solution using them. So that solves our complete problem. So to summarize, because it's important, that what we do, how do we begin, and what we do in solving quantum mechanics, a quantum mechanical problem. So first of all, somebody gives us some initial condition, psi x 0. Somebody tells us that this is whatever system, a particle in a balloon or whatever, I don't know. A system is in this initial state. Just like, in classical mechanics, we say the particle at t equal to 0 is at origin. And it has a velocity, this. And then you are asked to, find out what is x of t for later time. I give you x of 0 because somebody should give me the initial position, right? And then I can tell, okay. And then they give us the v of 0, these two numbers. And then we apply Newton's law and we find, using them, the general x of t for all time. Here the question is a little bit different. Here only thing provided is psi x at 0. And they ask us, after time t has elapsed, what is the general state of the system? What is that? That's the only question quantum mechanics asks. Okay, so the strategy is very simple. First of all, you solve time-independent Schrodinger's equation. Okay, which is just h psi of x equal to e psi of x. Okay, just remember this and you will remember always the, and remember what is the momentum operator for one dimension. And so you solve this equation. What you find is a series of these things. Psi x corresponding to that, a particular, Okay, you solve this, psi 1x, and you get psi 2x, psi 3x, some infinite series, So you basically get a series of psi nx. This is what you get when you solve Schrodinger's equation in general. Then this can be used. So you have some, as I said, maybe sine 1x, sine 2x, sine 3x, sine 4x, I don't know, like that, infinite of them. Then you can multiply this by, let's say, 2, this by minus 1.5, and that psi 3 by, I don't know, 5.1 into psi 4. Whatever you need to do, that's up to you. Choose these, tune these psi 1. So just put psi 1 and then, psi 2 plus psi 3 up to psi infinity, and then put some constant here wisely. They are like little knobs. Some of them could be even 0. Some could be negative, some positive. Some could be even complex numbers. Real, totally imaginary. Whatever you need to do that so that in the end you have this produced, this psi x of 0. Because x of 0 is just a function of x, right? At t equal to 0, so t will completely vanish from whatever that is. So choose your, because these are known functions, you have solved the Schrodinger's equation, found these psi's. And now, I told you that if you really tuned wisely, you can reproduce this function, any function. So this function has a shape, right? This could be, I don't know, this could be like this. Okay, this could be like this. And then choose like, okay, so this one looks a little bit like this. So I'll take a piece of this, and then I'll take maybe another one with slightly tuning less amplitude, and another one that looks like this, so a little bit different amplitude. So you keep adding them with different varying amplitudes. Maybe, okay, I need to do this one in the opposite direction. So that means multiplying by a negative number. In the end, by taking sufficient number of these things, in principle infinite of them, you will be able to produce whatever the function they gave you in the beginning. Okay? Time over hoiche naki? Tomalogar class ase? Class nai? Okay, olop tetia continue korim. Otto etia class nai. Okay. So very important, okay? This is very important. These are the functions that you calculated, so you know them. They could be exponential, they could be sine or cosine or anything, but these are known functions. Okay, and I'm telling you that if you have infinity of them, you can tune them and add them to produce any function. So why not this function? Okay, once you have tuned and you say, okay, now I have chosen this constant C1, C2, C3 and C of infinity. I have found these numbers such that if you multiply them by these particular numbers and add them, you will have this function. Okay, if you don't take infinity of them, if you take only a finite number, this match will be approximate. Okay, if the n is not infinity, let's say, then this match will be approximate match. So maybe this will look like some, wiggly thing here, almost match. But if you really took n, all of them, n going to infinity, then you can produce that perfectly. Okay? Now you have them. So you can write them as so this is what? The function that you produced by tuning and matched with the initial condition they got. They got you. Okay? And I am now asserting this, that once you got a match with the initial condition, all you need to do is how it evolves in time. How it evolves in time. And that time evolution of this thing is the complete function. And that is very simple. This, whatever CNs you have got, right? All you need to know is these CNs, C1, C2, C3. You found them. It will be just this, times psi n x, and nothing but these pieces corresponding to your each psi1. So if it's psi1, it's particular IE1 P by H cross. You know psi1, then you know what is its energy corresponding to this. Is this E1? For psi2, this is E2. For psi3, this is E3. And so just multiply by this particular, for psi1 this one, for psi2 this two. And if you did that, you produce for a future time what will be the wave function. And that's it. You solve the Schrodinger's equation, the complete solution. This will be the complete solution of the time dependent. How we started? We started from solving the time independent function. We found a series of psis, psi1, psi2, psi3. We actually tuned them, added them, produced the value initial condition given to us. And then we just multiplied by the wiggles. And we got absolutely the final solution of time-dependent Schrodinger equation forever. So that's it, really. So all we need to do is always, we will be given only a really space-dependent, potential. And so this strategy will work. And we'll solve this. So particle in a box, I'll continue this. So in the next unit, and harmonic oscillator maybe, whatever we have, we'll solve all of them. And every time we'll follow this strategy. Okay, so I'll give you some problems based on these all the things that we have done. Okay.